Several students requested that I show an example and give a detailed explanation of setting up forces on a mass spring damper system. So here are a couple masses stacked on each other connected with springs and dampers, and the lower mass is connected to ground with a spring and a damper. Noting that Y1, when Y1 is 0 and when Y2 is 0, there's no deflection in the springs. That would say that when mass 2 is at its origin and mass 1 is at its origin, there's no spring force acting on the masses. In order to formulate the forces, I suggest drawing the system in some semi-arbitrary state. So in magenta, you see here mass 1 is drawn where its position has moved up to 1 meters relative to the origin. That means that spring 1 is stretched and is pulling down, so I drew the spring force down. In order to formulate that force then, I create the formula, which is the spring deflection times the constant, and check the sign. So if Y1 is positive, plugging it into that equation, Y1 K1 would be a positive value. Of course, that magnitude is acting down, indicated by the vector there. So what about the damper? At that same state, I've indicated that the velocity of mass 1 is 1 meter per second, so the damper would be tending to try to slow that mass down. Okay, so I've drawn the vector down and I've formulated the damper force as being C1 V1, checking the semi-arbitrary condition, plugging 1 meter per second in for the velocity, we get a positive number. The vector's indicating it's acting down, so that works out okay. If the velocity should become negative, of course our vector's drawn down, so we would need to get a negative value here, and that would be the case. So moving to the other spring and dampers, mass 2 has moved more than mass 1. Mass 2 is at 2 meters away from its origin, and velocity 2 is 2 meters per second. So it's traveling upward at a higher velocity than mass 1, and it is stretched the spring because Y2 is greater than Y1, so there is stretch in spring 2. If there's stretch in spring 2, then the force would be acting up, and you could compute the value of that spring force by taking the product of K2 times the quantity Y2 minus Y1. Likewise, the damper force would be C2 times the quantity V2 minus V1. Plugging in those semi-arbitrary points, we'll get positive values for both of those expressions, and that magnitude is acting up for that condition. If things were to reverse and Y2 was smaller than Y1, then this quantity K2 times Y2 minus Y1 would be negative, and in our equations of motion, that would create a negative value there, reversing the direction of that force in our equation of motion. So moving on to mass 2, these forces are going to be equal and opposite, so if you've determined the correct formulations and directions for the forces on mass 1, you simply have to reverse those for mass 2. Now, if you want to formulate Newton's second law for these masses, that's relatively easy. We just simply have to come and add our body forces. So here is M2 times G, and here's the body force acting on mass 1. That's going to be M1 times G. And then our equations of motion, sum of the forces equals mass times acceleration, and we'll do these in the y direction. And we'll have minus mg minus k2 times y2 minus y1 minus c2 times v2 minus v1 is equal to m. We're doing this equation of motion for mass 2, so that'll be m2 times x2, we're working in the y coordinate, so this will be y2 double dot. That's the acceleration of mass 2. in the y direction. And placing our subscript on this mass, of course, that was supposed to be mass 2. Moving on to mass 1, we'll have minus m1g plus k2 times y2 minus y1 plus c2 times v2 minus v1 minus k1 y1 minus c1 v1 is equal to mass 1 times the acceleration of mass 1, which we will express as y1 double dot. I hope that helps get you started with mass spring damper problems. Good luck and have a great day.